Our last section of chapter 20 here talks about direction of chemical reactions. And when we talked about directions of chemical reactions before, we were really talking about equilibrium constants. And so really this section is about relating the spontaneity or the delta G of a reaction to where you're at compared to where you want to be. So remember when we talk about Q, that's kind of saying here's where you're at, a snapshot of your concentrations that you have. And K is the concentrations that you want to be at equilibrium. And so kind of some concepts to think about here is when Q is not equal to K, when you are not at where you want to be, the sign that you have for delta G depends on the position of Q and reflects the direction of the reaction as written. So let's see if this makes sense. For example, if Q is less than K, right, we learned in chapter 17, that means that we are before we've reached equilibrium. And looking at kind of one of these figures here, for before we reached equilibrium, we can continue to slide downhill to get to equilibrium. So that is the sign that we have of delta G. The slope of the line as we move forward is negative. So for the direction as written, you've not yet reached K, we can continue to slide down. If Q is greater than K, the sign of delta G, which really reflects the slope of the line, is positive. So if we are past our equilibrium point, the slope of this line now becomes positive, since we're considering it for the reaction as written. You've moved past K. You've driven past your destination. The only way to slide back down and go spontaneously back to K is we have to reverse the reaction. And reversing the reaction, again, allows it to be spontaneous. If Q again is equal to K, you are at equilibrium, delta G will equal 0. You are at where you want to be. So the idea is that the sign that we have for delta G depends on where Q is as compared to K for the reaction as written. If Q is less than K, delta G will be positive. If Q is greater than K, we've gone past our equilibrium, the delta G will be positive. The only way to have delta G be negative and to slide back down is to reverse the reaction that we're in. So that has to do with the sign of delta G. Again, Q not equal to K, the sign of delta G will tell us kind of where we're at. The extent of the difference between Q and K is the magnitude of delta G. So if you're just kind of a little bit away from K on either side, again, before K it's negative, after K it's positive, but if you're just a little bit away, if Q is almost equal to K, then delta G is going to be a small value. You don't have too far to go to get to be where you want to be. Okay, where you're at is not far from where you want to be. However, if you have Q that's very distant from K, you have a huge distance to travel, which in terms of the magnitude of delta G is going to be significant. I always like to think about a slingshot analogy here, right? So I'm going to use my hands here. Imagine just having a slingshot and you just pull it just the littlest bit and then you let go, right? You're really not going to go too far. It doesn't have a lot of thermodynamic driving force, let's say. However, if you pull that slingshot back really far and it's nice and tight, and again, the difference between my hands represents where you're at, Q, where you want to be, K, when you let go, there's a lot of driving force to pull you towards that. Okay, so conceptually, that's what I want you to think about. We're going to look at sample problem 20.9 right now with that same kind of an analysis. We're going to do it a little bit differently from what the problem kind of directs us to do, only because I think there's some things that are overly complicated to think about from a physical chemistry standpoint, a P-Chem standpoint, that we're not going to get into, but I still think we can take some things from this molecular scene problem. So again, this molecular scene has diatomic gases, A2 and B2, that react to make two molecules of the mixed diatomic gas, AB. Tells us that the delta G naught for this process, again, this naught means standard state, is minus 3.4 kilojoules per mole. They tell us that mixture 1 is at equilibrium, and so we know mixtures 2 and 3 are not at equilibrium. So again, I'm going to change how this is written here. We're going to keep problem A the same, but we're going to change B to C, and then just say we're going to evaluate delta G for mixtures 2 and 3 and for standard state, which is really what part C means. Okay, standard state, where all concentrations are 1 atmosphere. So again, standard state means all partial pressures are equal to 1 atmosphere, or if you're dealing with concentrations, all concentrations are 1 molar. All that really does is mathematically make your K or your Q equal to 1, right? Because if you put in concentrations of 1, doesn't matter whether you square it, multiply it by a ton of other ones, the answer is still going to be 1. So we're just going to look at this problem a bit qualitatively, and then what we're going to try to do is kind of map onto one of these pictures where we're at. Okay, so let's kind of do the first part here and think about calculating what K is equal to. So what I'm going to kind of set up here is a table underneath these, and I'm going to consider then a last column here for when things are what we call SS, or standard state. So I'm going to write the partial pressure of A2, partial pressure of B2, partial pressure of AB, and then we're going to calculate Q from this. Right, so here's our reaction. So if we're going to write Q, Q is going to be equal to the constant, well, we're going to do partial pressures here. The partial pressure of AB squared over the partial pressure of A2 times the partial pressure of B2. Okay, so what I'm going to do here is they tell us that in these molecular scenes, if I count molecules, each molecule represents 0.1 atmosphere. So for example, in this first one, I have 2 of the A2 molecules, which are these black molecules. And if I multiply that by each one being 0.1 atmospheres, I have 0.2 atmosphere is what the partial pressure is of this. So I'm just going to go ahead here and fill out the rest of this table. And once I fill out these values, I'm going to calculate my Q by putting these values into here. So when we are at equilibrium, which they told us that mixture 1 was at equilibrium, K is equal to 4.0. So what we know is that we slightly favor products at equilibrium. So what I'm going to do right now is I'm not going to talk through all of this. I'm going to go ahead and fill out the rest of this table for mixture 2, mixture 3, and then standard state. They actually tell us that our concentrations are 1 atmosphere. Well, again, as you can see, that means we've got 1 squared over 1 times 1. That's equal to 1. Okay? By definition, Q will equal 1 at standard states, because whether you're putting in concentrations or molarities, everything's going to be a 1. All right, so let's go ahead and do the rest of these. I'm going to have 0.3 atmosphere, 0.3, 0.2. Put this into this expression, 0.2 squared over 0.3, 0.3. We get 0.44 for mixture 2. In this case, Q is less than K. Okay, we are before our equilibrium point. So we already talked about before the equilibrium point, delta G is going to be equal to a negative value, right? If we kind of think about this, if we're before the equilibrium point, we're still going to slide down to get there. Mixture 3, 0.1, 0.1, 0.6, 0.6 squared for 0.1, 0.1. Q is equal to 36 for mixture 3. So in this case, Q is greater than K. We are past our equilibrium point. There is no way we can continue along this path and get to our equilibrium point. We've walked too far. So delta G in this situation is actually going to be positive. This system has a positive delta G because we have pushed it past where it wants to be in terms of the reaction as written. We can have this be negative and it can slide back down to the equilibrium point, but that means that the reaction needs to reverse. There is no way that we can continue to have this reaction proceed as written and get to our equilibrium point. We've passed it already. The only way is we have to reverse this process. AB molecules need to decompose into A2 and B2, and then we can slide back down. So what I'm going to try to do here is just kind of sum that up by making kind of our own plot that looks like this for each of these situations. So remember, mixture 1 was Q was equal to K, which was 4.0. Mixture 2, Q was less than K, and Q was equal to 0.44. And mixture 3, Q was greater than K, and it was equal to 36. So let's see if we can kind of draw a plot here that sort of makes sense with what we're talking about, right? So I've got a situation here where I know this difference here represents minus 3.4 kilojoules. So delta G, again, representing the difference between products and reactants, minus 3.4 kilojoules, which is what we knew it was for this process. When I have reached my set point, when I am at where I want to be, I know that my equilibrium constant will equal 4.0, right? So that's what my K will be equal to. When we had our standard state mixture, right? That was when Q was equal to 1.0, right? So this again is our standard state mixture. So our standard state mixture, Q is less than K. We can still continue to slide down and get to product, or I shouldn't say get to product, get to our equilibrium point, okay? When we had mixture 2 had 0.44. So again, this is mixture 2. This guy was mixture 1, right? Again, with this case, we're going to have a situation where it's actually even more favorable for mixture 2 to go ahead and do that. And again, if we look at the thermodynamic driving force for standard state going to equilibrium, this is going to be minus 3.4 kilojoules. For mixture 2, continuing on, and we're not going to walk through the math for how you get these numbers, and I don't want you to worry about it. It gets into a little bit more complicated stuff to explain, and so I'm not going to worry about explaining it. But this has a little bit more thermodynamic driving force because Q is further away from K. Now again, for mixture 3, we have walked too far past K. We are too product heavy. What that really means is we can't use the same reaction as written and get less product and more reactant. That's not how that's going to work. So in this case, there's no way that we can, we essentially have this guy represents a positive value, positive 5.4 kilojoules. We can't get back to this point going downhill unless we reverse the reaction. So if we want to go in this direction, the only way to do that is to reverse the reaction, which again, for this chemistry means that two ABs are going to have to break down into A2 plus B2. And hopefully maybe you remember from chapter 6 when we talked about enthalpies and you talked about how to manipulate enthalpies of a reaction. Well, we can manipulate delta G's in the same way. So the delta G for this process is actually going to be positive 3.4 kilojoules per mole. Okay? This process is going to be the negative of that. But again, if we're trying to approach it from this direction, and we are at that point having Q less than K, we're actually going to be okay to do that if we've already kind of gone past it in the forward direction. So I know this is kind of complicated to think about. I don't want you to overthink it. Again, a few important things to remember is that the sign and the magnitude of delta G have importance, right? The sign of delta G depends on whether the reaction is spontaneous. And again, the reaction will continue to be spontaneous if you haven't yet got to equilibrium. If you've gone past equilibrium, the sign of delta G is going to be positive because you've gone too far. The only way to make delta G be negative and have you go back to K is to reverse the reaction. So the sign of delta G is important. The magnitude of delta G is also important. And again, that has to do with the difference between Q and K. If there's a large difference between Q and K, you're going to have a large magnitude to your delta G. So again, two parts to delta G that are important, the sign and the magnitude. Sign indicates spontaneity. Magnitude kind of indicates the strength of your thermodynamic driving force, right? Think about our slingshot and whether or not we're having it just pull a little bit or we're pulling a lot. Again, really not anything computational in this problem, a lot of conceptual stuff to think about, but important to think about with free energy, which ultimately determines reaction spontaneity.